In this video, I'd like to revisit the blink Millis sequence of sketches that we've been going through, and to go back and address an issue with the code as we've developed it so far. And that has to do with the overflow of the Millis timer. So I have here running just the basic blink Millis 1 sketch, where we're flashing at 1 Hertz. And just remind you of how this works. We initialize in the setup method, we initialize a global variable blink time after we've set the LED pin to high. We look up the time on the Millis timer and store that in blink time. And blink time represents for us the time that we last changed the state of the LED. And so in the loop function, what we're doing is we're checking the value of the Millis timer, and that's t. And if t exceeds blink time plus blink interval, then we're going to flip the state of the LED and then store the current value of the Millis timer into blink time. That represents the new time origin that we're looking for the next increment of time. And this will run quite nicely for 2 to the 32nd or so milliseconds, which works out to be about 49.71 days. But if your code runs longer than that, what will happen is that when the Millis timer gets up to 2 to the 32nd minus 1, which is the largest number that you can represent with 32 bits, the next time it counts, when the clock ticks, 1 millisecond later, the value of t that we would get will wrap back around to 0. And so we're going to be looking for a number that is quite large, and the value of t will be quite small. Being down near 0, it'll be a very long time again before we get back up to exceed this very large time that we're looking for. And so we want to develop some way of addressing that so that we can blink our LED through that 49.71 day period and not miss a beat, so to speak, or not miss a blink. So it's easy enough to detect when the overflow happens. All we have to do is make sure that, or to see if t is less than blink time. So if t is less than blink time, then we know that the overflow has occurred. And so what we would like to do is develop maybe a more complicated condition to put in our if statement, so that if the normal case is holding, that t is greater than blink time, then we check this case. And if t is less than blink time, then we check some sort of different case that would handle the wraparound smoothly. And our goal is going to be to figure out what that condition is and develop a more robust way of dealing with this. Now, of course, your Arduino sketch may not be running for 50 days continuously, and it may just not be an issue. But we'd like to make the code a bit more robust. And so the condition that we have when the normal case ensues, that's when t is greater than or equal to, let's say, t0. t0 is going to be our origin, our time origin. And in this case, the condition we're interested in checking is the one that we have in the code right now, that t is greater than or equal to t0, let's say, plus capital T, where capital T is our time interval. This would be blink time in our example. This would be blink interval. But we might have other things that we're checking, and we might like to use a generic name here for these things. So the other case would be t less than t0. Okay, and in that case, the condition that we would really like to be checking is something more like t plus 2 to the 32nd is greater than or equal to t0 plus capital T. All right, so this 2 to the 32nd would represent the 1 in the 32nd bit position, numbering the least significant bit from 0. So when we have a 32-bit number, the ones digit is effectively the 0th bit when we talk about these things, because 2 to the 0 is 1. And then the most significant bit would be the 31st bit. And so this 2 to the 32 really represents the overflow into that 32nd bit position. And of course, that is not representable in 32-bit numbers. And so this T here represents the part that resulted in the wraparound, and the 32 least significant bits of the number. And this is sort of the extra piece that isn't accounted for, or isn't able to be accounted for in our 32-bit unsigned integers. But this would be the condition that we would need to check in the event that t is less than t0 and the wraparound has occurred. And so what we'd like to do is we'd like to manipulate this condition into something that we can check relatively simply with 32-bit unsigned integer arithmetic. And so what we're going to do in order to do this is we're going to move the t0 over to this side of the inequality by just transposing it. So we can subtract it from both sides, and our condition would become t plus 2 to the 32nd minus t0 is greater than or equal to t. Now this still is not representable in 32-bit integers, because this 2 to the 32nd is not itself representable as a 32-bit integer. And so what we're going to do is we're going to add 0 to the left-hand side of this inequality by adding and subtracting 1. We can always do that. So this would be t plus 2 to the 32nd minus 1 minus t0 plus 1 is greater than or equal to t. Now, everything over here, actually, if we take this 2 to the 32nd minus 1, now this would be the largest integer that's representable in an unsigned 32-bit integer. And so we could just figure out what that number is as a decimal number. I don't have it memorized, but we could easily figure out what that number is. We could just put that in as a big long number that's up near 4 billion or something, and we could do the subtraction, parenthesizing it first to make sure that that result fits inside a 32-bit number, and then add t to it and add 1 to it and see if that exceeds capital T. But we're going to do one thing which I think is actually a little nicer, and that is we're going to replace this thing in parentheses with a bitwise operation. So my claim to you is that this is equivalent to the following expression. So this tilde in C or C++ represents the bitwise not operation. So a bitwise complementation. So we're taking the bits in T0 and we're changing all the zeros to ones and all the ones to zeros. And my claim is that when we do that, that is entirely equivalent to the subtraction operation. So 2 to the 32nd minus 1 minus T0. And so this condition should be equivalent to this condition, except we don't have to worry about representing numbers that are larger than would fit in a 32-bit unsigned integer. And so our overall condition would be something like t greater than or equal to t0 and this condition, or t less than t0 and this condition. Okay, so I want to just show you that this equivalence holds, and then we'll develop a little helper function that will implement this slightly more complex Boolean expression so that we don't have to have if statements with very long Boolean expressions running around our code. We can just call the helper function, and then we'll test it out. So let's consider some number x, which is an n-bit number, and we can represent that as generically a binary representation where we have the sum from I equals 0 to n minus 1 of some b sub I 2 to the I, where bi is an element of the set 0, 1. So these are the bits in the binary expansion of the number x, and they're weighted by a power of 2, and x is represented by the summation of those things. Okay, so now let's consider the complement, the bitwise complement of x. So tilde x would be equal to, again, a binary number, I equals 0 to n minus 1. And the bits are going to be, if you think about it, if we know that the bi are the bits in x, to get the complement of the bi, we can just do 1 minus bi. Right, so we want to interchange 0 with 1 and 1 with 0. So if bi is equal to 0, then 1 minus bi is just 1. Whereas if bi is equal to 1, 1 minus 1 is 0. So this 1 minus the bit is equivalent to taking the complement of the bit. And that's again going to be weighted by 2 to the I. And now we can just do some simple math on this. So if we like, we can distribute the 2 to the I through this difference here. So we can distribute that into the parentheses, and we can break this up into the sum of two things. So this is the sum I equals 0 to n minus 1 of 2 to the I. That's the 1 times 2 to the I. And then that's equal to, the second term is minus the sum from I equals 0 to n minus 1 of bi 2 to the I. Well, this thing here is just x. Right, so this is x. And this thing turns out to be 2 to the n minus 1. So this is just an arithmetic sequence, or I'm sorry, a geometric series, and the common ratio is 2. It's a finite series, and there's a formula that you can use to find the sum of that. You can pretty well convince yourself that this is equal to 2 to the n minus 1. Another way to see this is that this number has all of the bit values equal to 1. And so this would be equal to 1, 1, 1, 1, 1, 1, 1 n times. So there's n 1 bits, and that would be the largest number representable by n bits. And so that would be 2 to the n minus 1. And so this is exactly what we had in the case of our condition, where here n would be 32 in that case. So we have 2 to the 32 minus 1 minus t0. So t0 is here x, and n is specialized to 32. But this holds in general, and this is kind of, I think, a somewhat more efficient way of doing the computation than subtracting t0 from that magic number that we would have to do. So in figuring this out, it also struck me that we're going to have potentially another issue that would happen just slightly before the rollover issue with the Millis timer, the way that we've actually set up our if statement in the original code. And that has to do with the fact that blink time plus blink interval could actually very easily be larger than would fit in a 32-bit number. And it struck me that if that's the case, then what might happen is that the right-hand side of this inequality might well roll over and wind up being kind of a very small number. That would happen when, for instance, blink time is within blink interval of 2 to the 32nd, and so that the sum would exceed 2 to the 32nd, and t might be some very large number that may not be in excess of blink time plus blink interval, but still, because this is rolled over on the right-hand side, this test might pass and it would start to execute this toggling of the LED much sooner than it actually should. And so that struck me as a potential issue with the way I formulated this if statement. And to test that idea out, it occurred to me to just write a little test script that would kind of set up this case so that we didn't have to wait around for 49.71 days for this case to arise, waiting for the Millis timer to increment up that high. So to do that, I basically created this sketch where I've initialized blink time to this number, which is basically 2 to the 32nd minus 100. So that when we add this number plus blink interval, which is 500, we're guaranteed to be in excess of 2 to the 32nd by 400. And then I made t, another large number, which was 2 to the 32nd minus 50. And so this is still a number that fits within a 32-bit integer, unsigned integer, and it does not. It should not. I want to make this the way it originally was. Flip this back. Okay, that was the solution to the problem that occurs. But to figure out whether it was a problem, I had the code set up this way, where we're looking for this number here to see if it's larger than or equal to this number up here plus 500. So obviously, the way I've got these numbers set up, this test should fail, and we should not go in here, and we should execute the green LED. So we should turn the green LED on if we run this code. And so let's push this out to the board and see what happens. Oh, the red LED turned on, which means that we went into the body of the if statement rather than the else clause. And so that's a problem. So that tells us that, yea, verily, the right-hand side here has a problem where it will overflow and wrap back around to through 0 to some low number sooner than we'd like. And so the solution to that is to basically move this to the other side. And so we can just transpose this over to here and look at t minus blink time to see if that's greater than or equal to blink interval. And if we push that out, now we have the correct behavior where we are expecting the green LED to light up, and indeed it does. So what we'd like to do is to use this form of the test in the usual case, and then we'd like to use our alternative expression involving the bitwise complement of t0, adding that to t plus 1 in the case where the overflow has occurred. And so what that looks like is, let's see, this. So what I've done here is I've created a helper function which returns a Boolean, and it's called itIsTime. And it takes t, t0, and dt. dt is our interval, and t0 is our time origin, and t is the current value of the Millis timer. We pass those things in here, and we just return this condition. So this first part handles the usual case where here t exceeds t0, and we're testing t minus t0 is greater than or equal to the time interval dt. The second piece, which we're ORing together with this one, ensues when t is less than t0. And in that case, we're adding t to the complement of t0 and 1 and seeing if that sum exceeds dt. So you may be concerned that evaluating this whole expression takes a lot more time than the original one did. It turns out that that's not really the case, because these logical operators in most languages, including C and C++ and Java and Python, are what are called short-circuiting operators. And so this is an OR. This double bar here is an OR. And so if you know that the first disjunct in this two-way OR operation evaluates to true, then the whole expression will evaluate to true, and so there's no need to evaluate the second half of the expression. Likewise, if you have an AND, if you evaluate the first conjunct in the two-way AND operation and it works out to be false, then there's no need to evaluate the whole thing, because you know the overall piece of the expression will be false, because in order for an AND to be true, you have to have both conjuncts to be true. That's kind of the opposite for the OR. In order for an OR to be true, all you need is one of the two disjuncts to be true. So it will only, in the normal case, evaluate this piece of the expression, which has the test to see if t is greater than or equal to t0 in it, obviously, but that's a little extra overhead. But the fact that this actually will handle the behavior through the transition, through the rollover in a seamless fashion, I think is well worth the little extra complexity in the evaluation. So the if statement down here becomes, if it is time, t, blink time, blink interval, then flip the LED and remember the current time and blink time. And so that's a very natural way. You can almost read it as if it were written in English by the way that we've named our function. So if it's time, then we do the stuff. If it's not time, we don't do the stuff. And so we can push this out, and we get the blinking behavior that we expect. Unfortunately, this isn't telling us whether or not it's going to give us the correct behavior at the rollover. Otherwise, we'd have to sit here and watch it for 49.71 days and catch the cycle during which it supposedly rolls over, but our thought process is that that should be completely seamless, and we shouldn't be able to detect that by looking at the flashing. If it were to do some weird behavior where there's some underflow or overflow rather, and you get a bunch of flashes in a row and then it stops blinking, that would be an indication that something's not working properly. But we've supposedly made the code more robust, so it goes through that transition without really missing a blink, as I mentioned. And so how are we going to test this? Well, we can test it in a way that's similar to the way that I tested the whether or not the right-hand side of our original way of phrasing the condition was subject to the overflow problem. And that's by creating a test case, and along similar lines to the one that I did here in this little program sketch called foo. So I've got another one I'm calling bar, which uses our same helper function here. And I've set up blink time to be 2 to the 32nd minus 100. and I've set up blink interval to be 500, and I've set up t, a number of different cases for t. So the first case is t is equal to this 2 to the 32nd minus 50. And this was the case that failed before, and we expect the green LED should light because it's not time yet. So, but in this case we've engineered these numbers so that the blink interval plus blink time will overflow, which we've supposedly addressed by this mechanism, and so we should get the green LED lighting up if we push this out, which we got. So that's good. So we can comment out this one, and we can try making t 50. Now in this case, we're not yet to the proper time, because in order for us to be more than blink interval, more than blink time, we have to go the 100 that we have left to go before we hit 2 to the 32nd, and then there's 400 left, and so we shouldn't be in the condition where this is time yet, but we are in a condition where, if you like, we've overflowed the Millis timer. We're simulating that condition here, and so we expect the green light should turn on. And it does, about that. Okay, so now our third test case is we make t 500. So 500 should be should exceed blink time plus blink interval. So the 100 that we have left to get to 2 to the 32nd, and then you subtract that off of blink interval, so the 500 should exceed basically the 400 and that's left, and so we should see, in this case, the red LED light up, and it does. So that's a good indication that our condition holds. Obviously it's not an exhaustive test, but at least it gives us some confidence that that our now new and augmented way of checking for this is on the right track here, at least. Okay, so that's it for now. The latest version of Blink Millis, Blink Millis 6, is in the repo, so you can take a look at that. You can grab this helper function if you would find it helpful for your own code. You're welcome to use it. Anyway, thanks for watching.